Friday session, just send them either to me or to Ani Krishna or to Nicola Del Foss, or submit them through our Zulipad. Okay. Our next speaker is Michael Beverland from IBM Quantum, and he's going to tell us about On the Hook for QC blueprints. Thank you.
Hey, everybody. Can you hear me okay? Great. So yeah, this is work. I'm at IBM Quantum now, and this is work that I did when I was still at Microsoft. I did it with Vadim Klichnikov and Shilin Huang. And what do I mean by on the hook for QC blueprints? Well, I think it's kind of helpful sometimes to take a step back and think about the whole quantum computer, and to think about a kind of a stack picture with something very abstract at the top where people are writing new algorithms, and something very explicit at the bottom where we really have hardware that is built in the lab. And our job, what are we on the hook for in the quantum error correction community? We're really responsible for this middle piece here in the middle of this stack, where we are supplied with qubits that are somewhat abstractified, but we are promised that our physical qubits have some properties. We treat them as little black dots, but we assume that they have a certain connectivity, a certain quality, and that there's a certain number of them. And we are responsible for somehow putting those together and using them to produce some logical qubits, which have some, again, connectivity, some set of operations, and some quality that we promise those logical qubits will have. And we are on the hook for filling in this layer and solving this problem and providing the blueprints to do that. And if we don't, then the quantum computer won't work. So what I would like to talk about today is something to help us with that, and that's essentially tools to help design and prove that logical operations are fault tolerant. And the basic idea is these are some set of logical gates that we might want to be able to implement. You could have other things there as well. And each of these is going to be implemented in some potentially very complicated hardware operations that needs to achieve those logical operations. Like the S gate, for example, might look like some complicated thing like that. You'll have some different complicated hardware circuit to implement each of these. No. And what I would like to talk about today is tools in order to help us with this process. So first of all, we want to be able to verify that one of these complicated circuits, maybe one that's actually real rather than made up, as Steve pointed out, does what it's supposed to do, and that it is fault tolerant, which we'll come back to. But what we'll mean by that is it is able to correct up to some fixed number of faults in some specific noise model that occurs in the entire operation. We're also going to want some tools to help us to modify a circuit if it doesn't do that. If we start with some attempt at designing some circuit and then find it doesn't work. And we also want to ensure that our hardware circuits remain fault tolerant when plugged together. And this comes back a little bit to some things that Jungwon was discussing today. It's not enough for each of these to be by itself fault tolerant. We want to make sure that whenever we plug them together, any large circuit can still perform reliably for up to some number of faults. And the main results that I'm going to talk about are, well, 3 tools in a Hadamard. The main tools are a convenient fault tolerant definition, so a definition of fault distance. And this is quite similar to other things that are already existing in the literature, but the way that I'm going to show you, I think, has some advantages, mainly in how convenient it is to use. A composition property, I won't actually discuss that today, but a composition property that allows you to ensure that if you have different logical operations, then if you prove that each of them is fault tolerant and they satisfy this time local composition property, then you can plug them together and the overall circuit will also be fault tolerant. And also, and I think this is kind of the main thing that I would like to talk about today, is a generalized notion of what a hook error is in fault tolerance. This is something which is very important for circuit design, and I think that having a rigorous, more general framework for this is something that is going to be useful in my own work, and I would like to tell you about that today. And then an application of these ideas to design a new fault-tolerant gate for the service code, which is an explicit implementation of the Hadamard. This is very similar to another work that came out at around the same time, actually a little before, although Shilin produced this much before that came out. Okay, so this is, don't worry, you don't need to understand this. This is another stabilizer circuit, because I'm going to be talking about stabilizer circuits today. So what I mean by a stabilizer circuit is just that you have preparations of things like basis preparations, but also potentially plus state preparations. And so eigenstates of Pauli's. You have Clifford unitaries like C naughts. You have measurements, and those measurements can, the outcomes can be used to control other things. So you record the measurements and then apply the classically controlled Pauli's on the circuit. So this is what we're going to think about as a stabilizer circuit. And then a stabilizer channel is a circuit built out of those operations, which takes you from some input stabilizer code to some output stabilizer code. They do not need to be the same code, but that is the promise. If you have a stabilizer circuit that's a stabilizer channel, then for some fixed input stabilizer code, it will always output some fixed output stabilizer code. And this is very, very general. I just want to kind of give an indication of that. Although this seems like it's something that's applied to logical operations in a stabilizer code, it also applies to many, many other things. For example, fault-tolerant error correction and logical Clifford operations in not just surface codes and color codes, but all stabilizer codes. But also, because we can have different inputs and outputs, this applies to Floquet codes, and it also applies to any, as an LDPC code is a stabilizer code, any LDPC codes, and also concatenated codes. It's really very general. What it does not include is non-Clifford operations. And while that is a limitation of what I'm going to tell you about today, it does play with non-Clifford operations. And that's because notice here that you have some free input, some unspecified input, which can be an arbitrary state to these logical operations. So for example, if you have some other T state that's been produced that you have independently verified has some quality, then you can plug it into this framework. But we don't have a way of analyzing a circuit which has non-Clifford operations within it by itself. Okay, so I want to introduce some formalism. I think this is actually probably for most people the most useful part of the talk is the formalism itself. And just for some initial intuition, imagine a circuit like this. And we're going to consider some noise model. And for that, we need to specify what the faults are, what faults can occur. And so, for example, faults will consist of some specific event that can occur in the circuit. That could be, for example, a Y, some Pauli operator being applied here. It could be some fault on a 2-qubit operation that would be like a Z being applied to the support of that afterwards, these kinds of things. So some Pauli operators that can be applied. It can also be the flip of outcomes. There will be measurements in these circuits, and it could be that those outcomes are flipped. But really, we don't actually require any structure or locality or anything, as long as each fault is some specific Pauli operator that's applied at some point in the circuit and some set of flips to some outcomes in the circuit that can be included. And you can follow the effect of one of these kinds of faults through to the end of the circuit. So for example, this particular flip here, if that occurred, the blue one, that would introduce this classically controlled C0 to activate when it shouldn't, which introduces an X on that qubit, and it can be followed through the circuit to the end. And we are going to talk about checks. I'll come back to this in a minute, but a check is going to be some set of outcomes in the circuit, which are somehow combined together and their parity is taken. And those are going to be used to detect the faults that have occurred in the circuit. And we will use that to build a channel check matrix. For each fault, we have a set of all the allowed faults in the circuit. And for each of those, there will be some set of checks that are flipped by that fault, and we could build a matrix from that. And in this talk, I'm going to be thinking, although it's very general, I'm going to be thinking typically of circuit noise, which is a specific noise model like this, but where every operation has a random Pauli operator applied after it whenever it fails. Okay, so now I'm going to describe what I just described again, because I think it's very important, but I'm going to describe it a little bit more mathematically. And so channel checks are going to be parodies of circuit outcomes. So we just think of that in a general sense, but they should be trivial. So the parody must be trivial if no fault has occurred in the circuit, and that's going to define a check. And then the channel check set must be a complete set of all such checks in the circuit. There are many different equivalent choices, but you can change basis, but the set must be complete. And this also must include within it a perfect set of outcomes at the end of the channel. And this is a mathematical tool which needs to be treated very carefully. And in particular, when composing, you have to make sure that you're not cheating yourself by including that set of perfect operations at the end of the channel. Then the fault set is a set of all of the faults that can occur and their effect on the circuit, as we illustrated in the previous slide. And in this talk, each of these faults we will assume occurs independently with some probability p. And two faults can be equivalent if they have the same effect on the circuit. And in general, if that's the case, we just absorb them into a single fault. And so that produces this check matrix. And if you have some particular fault configuration that occurs, so you randomly sample from all of the faults, if you have some fault configuration that occurs, what you will observe is the syndrome obtained by just doing the matrix multiplication of the fault vector. Okay, so hopefully fairly straightforward. The other thing that we have to ask is, what do these faults do to the logical circuit? So ultimately, we're going to care if they make the circuit fail. So we need to think about what the circuit is actually supposed to be doing at the logical level. So something which is useful, we find useful, is there's a general form for any stabilizer circuit, and any logical stabilizer circuit can be represented in this form, where U and V are Clifford unitaries. And with this, we can then define the logical effect of each of the faults, in addition to just the syndrome of each of the faults. And that's, again, by a matrix relation. And so what is the logical effect? Well, if you look at this general form here, you notice that you can change the logical action of the general form only in a few ways by applying the kinds of noise that we described. You might change the logical outcome that you read from some logical measurement that occurs in your circuit, and that's this flip here, which is being introduced by the fault. You might also apply some Pauli, but notice crucially that a Z-type Pauli applied to this ancilla preparation at the logical level will do nothing. And so this logical action that we have here is the combination of these three things: the X-type Pauli, the Z-type Pauli, and then the flips of logical outcomes. And why this seems probably a little bit more complicated than most people who deal with fault tolerance are used to, and I will explain that now. The reason is because we're most commonly used to dealing with logical idle, and things are a little simpler. This is not necessary there. But essentially what's happening here is, if you do have logical idle operation or a logical unitary operation, then all that's really happening here, there's no measurements, then there's no logical measurements. All that's really happening is, if you have some fault configuration, it might change the logical operator that's applied at the end of the circuit. But if you have a measurement, a logical measurement, say, for example, you measure logical XX in your circuit, then there are two things that are different now that can go wrong. First of all, you might get the outcome of the measurement itself wrong. That's a new thing that can happen. It's not captured in the Pauli at the end of the channel. Another thing that can go wrong is that you might, the faults in your circuit might introduce a logical XX operator at the end of your circuit. And if you are only tracking whether or not there's a logical operator introduced to your circuit, you would think that that will make you go wrong. But of course, that stabilizes the action of a logical circuit, so you should not include that. And all that this, using this general form does is just automatically captures those things. Okay. There's another approach in the literature to dealing with this, to formally defining these things, and that's introduced in the logical blocks paper by Cy Quantum. And effectively what they use there is a choice state to describe the logical action. And they talk about these correlator functions, and what those really are the stabilizers of the choice state. Both are fine. I find ours more convenient to work with because it's easier to work with a circuit than a state that represents a circuit, especially when composing. Yeah.
Difference with detector error model from STEM, for example?
It's basically the same. So there, what has not been included is the possibility of other kinds of logical operations. But if you just fix to a unitary logical operation, then they are the same. Yeah. So just to kind of summarize and recap, once you have specified all of these things, so you have your circuit, you have the faults that are allowed to occur, you build these matrices, then the formalism is very well defined, and it's just linear algebra. You have, we can look for logical fault configurations. These are fault configurations that are invisible, taking the role of a logical operator for a normal code. And so they will have h.f being 0. There's no syndrome. And if they're non-trivial, then the logical action of them, L.f, will be non-zero. And then the fault distance is simply the smallest such set of faults. So which set of faults you can't see, but will do something non-trivial to the circuit. And the reason we would care about this measure, this fault distance, is because if you have a set of faults that occur that is less than half of the fault distance, then a minimum weight decoder, which just has access to these two objects as well, will be able to correct that. Okay, so how do these things calculate? How do you calculate these things? Well, in general, it's not known how to calculate this for an arbitrary circuit, but it is known how to calculate these things when the H matrix, the check matrix, is graph-like. And that just, by graph-like, I just mean you can find some basis of checks such that the checks become vertices and the faults become edges, so that each fault is only connected to, only flips 2 checks. And it's also efficient, even if you don't know whether your circuit is graph-like, you can check it efficiently and then find a check basis. These are not things that we introduce. I mean, they're minor modifications because we use a slightly different notion of general form circuit, but they're really already known. You don't actually need it to be a graph. You could do something weaker, but we didn't actually find anything useful when looking for the weaker conditions. And there are, I think, some interesting ways to bound in general this object, but yeah, in general, calculating it it can be hard. Okay, but in what's to come, what I would like is to not worry about this. I would like to assume that for whatever system we're working with, we have a way of, given these 2 matrices, calculating what the fault distance is. So we're going to have a black box. And there's a slight technical caveat that I would like to also be able to introduce slightly more general weights. So what I mean by that is, the way I've defined it so far, each fault can occur with the same probability. I would like to imagine that we have an algorithm that, and that's also fine. These are efficient for the graph. Yeah.
So I just want to be clear about the definition. So if the error occurs just before, after all of the measurements,
yes,
it's a single weight error.
Yeah.
Right? Wouldn't it be a fault that guarantees distance equals 1 for any circuit?
So in this framework, that would not be undetectable. Because in this framework, at the very end, and again, this is a mathematical tool for definition purposes, but at the very end of the circuit, you require that included in your syndrome is a perfect round for the output code. So if you had a single qubit error, that would be detect it and therefore would
You
not.
don't measure all the qubits, but you perform perfect code measurement.
Yeah.
So I don't think that this notion of distance makes sense once you introduce non-uniform weights. Because
No, it doesn't. It doesn't. So what I mean here by, so everything that I'm going to deal with in the talk formally is the definition of the distance. I'm going to need this as a subroutine to calculate things. But what I mean by that is you assign, instead of a weight 1 for each edge in your graph, you can assign arbitrary positive numbers and then calculate the minimum weight. That's all I mean. I want an algorithm to be able to do that, but I'm not claiming that's what I care about. Yeah. You'll see in the next slide. Go ahead, sorry.
Well, so if the hypergraph is a regular matroid,
Yeah.
How do you find the fault distance?
Okay, so I'll talk to you about it afterwards, but the basic idea is that you need the space that we care about to correspond to the cycle space of some graph, but that can occur even if the matrix itself is not corresponding to a graph. And that's so you do end up still with a graph and calculating for the graph, but it doesn't mean that the check matrix has to correspond to a graph. And there are examples of things like that. Yeah. Okay. Anyway, I'll skip. These are all maybe a little bit too technical. So before I go on, I actually wanted to describe an algorithm, a simple algorithm, which is a very general thing. And this is going to be useful for us, but I think it's kind of nice to just point out. If someone else has pointed this out before, I would like to know, but as far as I know, people have not specified this. But the idea is, suppose you have some algorithm capable of finding maybe it's a graph algorithm, maybe it's another one, capable of finding the fault distance of your system. And you have some particular fault, and you want to know, is this fault going to be a problem? Is this fault in a limiting logical operator? That's clearly a useful question. You could ask something even more general than that. If I have a set of faults, is that contained in some minimum distance logical weight operator? And so this is a simple algorithm to find the answer of that, as long as you can calculate the distance. And the idea is pretty simple. So okay, here's my little picture. So suppose we have, for example, some graph here, and the question is this pair of edges here in some logical fault configuration? And if we just run one of our normal graph algorithms to find the distance, that will find some logical fault configuration. They are constructive, those algorithms. And if it happens to include this, then we would know, yes, this is in a minimum weight fault configuration. But it might find a different one. There might be, typically there are multiple equal minimum weight fault configurations. So what we do is very simple. We run the distance checking algorithm a few times, but we introduce a new edge, a fictitious edge in our graph, which has a weight which is now 2 minus some small amount. And if the original edge was in a minimum weight configuration, then this now will be contained, guaranteed, in the minimum weight fault configuration of this new modified graph. And so we use this to check if any set of faults is contained in a limiting fault configuration. Okay, cool. So back to the big picture. So we want to use this, and I'll come back to some more details. We want to use this to design and prove fault tolerance of some logical operations. And it's useful to do that with the surface code, even though this framework applies for really anything, and that's kind of why any stabilizer channel, and that's kind of why I think it's interesting and something that I would like to work on in the future. So all of these operations that I wrote up there, we know how to do those in some sense fault tolerantly. If you have a distance D code, we know how to do all of those to protect up to some fraction of the distance. And what was not known before we endeavored on this work was how to achieve the distance for, say, the Hadamard gate. There are some specific gates that were known and some which were not. And this requires careful design of the circuit. So I want to talk now through, before I talk about the Hadamard, a slightly simpler case, which is the logical ZZ measurement, which is done by lattice surgery. And so the idea here, first of all, you can think about this in a topological sense. We have a pair of patches of surface codes here. We can think of those, if we kind of blur our eyes a little bit, as just squares with different boundary conditions around the outside of the square. And then we can think about the logical ZZ measurement of this topologically as just merging the two neighboring boundaries and then separating them again, splitting them again, which looks like this. And if we want to actually build a circuit to do this on hardware, then we need something explicit. So we just take some time slices of this and build those codes. So don't worry too much about the details here, but this is a kind of high-level circuit of how to do that. Each of these little squares is a measurement of either XXXX or ZZZZ, depending on the color. And the ones that are highlighted are not stabilizers whenever you perform the measurement. And so this specifies a circuit if you are able in your hardware to do these 4-body measurements. And just for a minute, let's think about a kind of noise model that we don't think is very realistic, but it's helpful for us to understand things, a phenomenological noise, where each qubit has an X or Z fault at each time step, and each outcome has some flip, can flip. That's our set of faults. And then the logical action of this, you can work it out using the general form that I described earlier. It looks like this through the merge and the split, which is, of course, the logical ZZ measurement. And the outcome of the logical ZZ measurement is the product of these shaded measurements here. So everything works and fits in with the formalism. If you want to actually find the fault distance for this, then you need to write those H and L matrices, right? And one way you could do that is each of these colored in checks is a check operator. If there's no faults, you'll get a +1 outcome for all of those because all of this is in the surface code. And if you do that, that is not a graph-like matrix. So you need to somehow recombine your checks to make a graph-like matrix, and you do that by taking products of a check one after the other. Okay, so you get a graph, and don't worry too much about the details, but if you check the graph using the algorithms we just described, you can verify that in this distance 5 code, if you repeat this number of times, it all does work. You need to repeat this number of times or you get the outcome wrong. Or you drop the distance because of the outcome being wrong. Okay, so that was for a kind of abstract picture, and I promised you I want to talk about hooks. So the idea here is that in a hardware where we can't perform those weight 4 measurements, we must build those from some simpler gadget, and that will form our circuit. And so these little gadgets look something like this, and it's well known that if some single fault occurs in the circuit noise model, that can result in a pair of qubit errors. And so if this happens, if a single fault occurs and results in a weight 2 error on our qubits, on our data qubits, then we call this a hook. And that's clearly problematic in some cases. And different circuits will have different sets of these hooks. So for example, okay, I've basically just defined a rule for what the circuit should be based on these little numbers A, B, C, D, E, F here. And what I'm doing in this next piece is I'm assigning some specific circuit. So this is not a fully specified circuit choosing these particular numbers. Don't worry about what they are. But the hooks that arise, if I choose that, look like this. So a ZZ hook fault will now be vertical and will line up with a ZZ logical operator. And so the distance that you will get if you do this is low. It's below what we would hope for. And so that's a problem. But you can choose a different circuit, and this is widely known. You can choose a different circuit so that this doesn't happen and your hooks are not problematic. And then you achieve full distance. But hooks are more general than this. The term hook, to my knowledge, was first introduced by the Dennis et al. Paper in 2002, a long time ago, for the surface code. And the notion of a hook is actually with respect to this model, this noise model that I described earlier, the simple noise model. And the point is, a fault in your circuit noise is considered a hook if it's built out of multiple phenomenological faults. And so, for example, in the where we have a graph and each phenomenological edge was represented, or each phenomenological fault was represented by an edge, you end up with a single fault, the faults that I drew up here, being a pair of edges, and they look like hooks, and that's why they're called hooks. And it's more complicated than that because you can have time-like ones, and it's a bit confusing. It's a bit of a mess, to be honest, when you start thinking about it all, and it seems quite complex, and that's kind of the point that I want to make here. However, it's very important. We just saw that if you don't do this, your logical operation won't work. So we have to think about hooks, but they are quite inconvenient. They're also they're used in many different areas outside also the surface code, where they don't really look like hooks anymore, but there's lots of contexts where these come up, and we would like to have something that's more general that we can use for any circuit, that we can use for Floquet circuits or anything, any stabilizer circuit. And so that's what we really would like to do. And so the generalization that I'd like to introduce, which is really very simple. We just define hooks with respect to a subset of faults. And that subset of faults can be any subset of faults in your circuit. And a hook is just a fault that's not in the subset. And so this recovers the standard definition when the subset is precisely those faults that are in the phenomenological noise model. So for the surface code, just to kind of give an illustration of this, if we have these circuits here, we have all of the faults on all of the different operations, then the subset is just choosing those which happen to be single qubit X and Z on each qubit and a flip, which is in there already. Okay, so we're not losing anything, we're just generalizing the notion, but it will be true that the fault distance for the full fault set will always be at most the fault distance of the subset of faults, the simpler set. Okay, and if there's a gap, then there's got to be some hook fault, some fault which is not in the subset that is responsible for that, or some set of them. And so when characterizing these things, these are ultimately what we were going to want to handle and deal with. Yeah, go ahead.
Sorry, but I mean, like if instead you had D layers of surface code measurements,
Which we do here, yeah. If we have that in mind.
With the subset correspond to like the, I guess it doesn't really.
You can choose any subset. Yeah.
Together with the check readouts that you get from each of the layers.
Yeah.
Because then you do have distance D, like default is D for the surface code, right? Like it saturates in that case. But you do still have hooks in that circuit in my, maybe it doesn't meet this definition of hook, but.
Yeah, so I guess if you have the fault set being the circuit noise fault set, and the subset being the phenomenological noise fault set, then it's precisely the same. There's no difference whatsoever. But maybe we can come back afterwards.
Keep going.
Okay, so what we would really like to do when designing circuits is to deal with these problematic cases. And first, I want to characterize what those are. So it's not as easy as you might think to characterize these things. And so I'm going to define two problematic faults. The first one is a brazen hook. And that's basically the kind of hook fault that we've already discussed, which is if you have some logical fault configuration, like this green vertical line, for the subset of faults, then if you have a hook, so some fault that occurs that is builds up a part bigger than one of that logical fault configuration, then we call it brazen. This is clearly a problem. This kind of fault will drop the distance for sure. So removing all brazen faults is necessary but not sufficient to make the distances match. But there's also other things that can occur. There are also other faults that can be responsible for dropping the distance. And we call these hazardous faults. And this is part of a minimum weight logical fault configuration for the full noise model. And so an example, just to kind of illustrate it, maybe unreasonable in practice to see this precise example, but in the full noise model, you might have a logical operator which is actually not a minimum weight logical operator at all for the simple noise model like this. This would be weight 7, and there are weight 5 logical operators here. But because of the hook, which is a weight 4 hook, a huge hook in this example, you could end up with this being a weight 4 logical fault configuration for this model. And so these can also cause a problem. This hook here is responsible in this noise model, where we have just simple single qubit faults plus this. This will drop the distance again. So we also need to worry about these kinds of hooks. But removing all of these it's kind of the opposite. It's sufficient. If you manage to remove all of these, then your distances will match. But it is not necessary to remove all hooks like that. Some of them are not problematic. And the point that I would like to make here, I won't explain exactly why, but this algorithm that we described earlier allows you to find efficiently, provided you can check the distance, it allows you to find all of these both. And so that's a very useful numerical tool if you're designing and building circuits and you want them to be fault tolerant. Okay, and I am pretty much finished with my talk. I just want to show some pictures essentially and give some very high level description of the Hadamard. This one I mainly wanted to show because I did this in PowerPoint by hand, and every time I show it, it reduces the cost for me per use. So, so here it is again. So this is an illustration of the circuit for the Hadamard. You could guess, of course, it's going to be very complicated. Just to kind of zoom in on one panel of this is a stage which is repeated d times. Oh, it didn't happen. Okay, supposed to get a zoom in there, it didn't work. But basically, what you can't see here is the little squares. The different colored ones are different circuits. And so you can kind of see, just glancing at this, 2 features. The first is that there is spatial variation within a patch. And this is clearly going to happen when you have a patch that's no longer a square or a rectangle. Now the logical operators can go around a corner. And so you're going to get some parts where the X-type circuit should be different because vertical hooks are bad, where in another region, horizontal hooks might be bad. But something that I think was not as expected for us was that you can have temporal variation. So here, for example, this is the exact same code, but you actually have to use different circuits for the same code for different periods. And that is because logical fault configurations can move in time, essentially. So you can have a logical fault configuration because you used to be in another code that prevents you from using circuits for a while that then become problematic because they don't jive with what you're going to do later. And so you have to actually split the round into 2 and use different circuits for the exact same code. And that's everything I wanted to tell you about. And I'll just kind of leave my conclusions here and maybe take questions if there are any.
So generally, so do I understand correctly that to design this kind of codes, you have some list of built-in tools that you are going to use, like ZN pattern measurements for surface code, and then you sort of to modulate it, you just apply them sort of. But now, do you do it by hand, or do you have tools to do it?
Yeah, well, I mean, so this work was done at my previous employer. You can definitely build tools with these ideas, and that is a large motivation for this work. Yeah, I mean, the way I see it personally now is if you have say the surface code, which we understand very well, then we kind of know roughly how to implement these circuits. So you try something, probably won't work, and you have tools to identify all of these problematic hooks, and then you see if you can fix them. That's kind of roughly the idea. For more general, like LDPC codes, then a barrier to using this framework directly is that we don't have an efficient algorithm to find the fault distance, because they are not typically graph-like. And in that case, I would propose using bounds to try to give you some indication. Some of the bounds are very tight. That's why I was asking you in the break about the BPOSD approach to find distance bounds, because those apply to any code, and I think that that's an interesting approach to proceed. Any other questions? Sorry. Am I supposed to choose the questions, or go ahead?
I guess you're interested in more practical things, but now that you have this definition of this hook distance and this fault check matrix, have you thought about writing down like a threshold theorem using, like, for example, Lehman's proof technique?
I think that this we did not discuss provable threshold theorems in this paper, but you can use these things. It's pretty close. Yeah, I think it's the condition that we require for this time local condition that we require for composition is, I believe, enough in combination with fault distance to prove a threshold. Yeah, but I don't know if they'd be very tight. But yeah.
It's nice to have some machine.
Go ahead.
So regarding like non-stabilizer circuits, like, do you think like basically just, taking out the Clifford group and like plugging in like C0 dihedral group or something, and then figuring out, say, like, kind of a stabilizer formalism with like C0 dihedral circuits would be enough to basically make all of the same analysis as possible, or is it a little bit more complicated than that?
It's a good question. The truth is I don't know. My guess is that even if you, so I hope for that is that, suppose you wanted to just analyze a circuit to produce a logical T state, then that itself is not a universal quantum computer. So you might be able to simulate that as long as you don't also combine that with other things. So you might be able to use that to simulate that in isolation. But then when you introduce the noise, that might break the efficient simulability, even if you have a way of doing it. But yeah, we can talk about it. Yeah.
That's the nice thing about the C0 dihedral group, is all your Foley noise would be basically in that group as well.
Yeah, maybe that would be very cool. I think it's something that I think would be really nice to include. Sorry. Yeah, please go ahead.
Yeah, so if we consider Newman with perfect matching decoder, the minimum distance is indeed the most important criteria. But if you consider big propagation decoder, there are many like arrows that are, I would say, with a weight that is less than the minimum distance that are also problematic. So we have this as a trapping sets for LDPC codes in the capacity model. And so I want to ask, is there any intuition of how like tracking cells in circuit level noise looks like?
A good question. I would say it's probably very code dependent. Trapping set. I mean, here. Well, I guess it's maybe a different thing. So when I think of trapping sets, I think of things that prevent your decoder from terminating, rather than things that cause faults. But are you thinking of something else? Are you thinking of?
Yeah. So I'm considering like what kind of, let's say, combinations of subgraphs in a stabilizer code and gate ordering on this stabilizer like management circuit, like how to say, what kind of combination of these two things like lead to some like typical errors that Billy propagation decoder fails. So with this information, it might be better to, how to say, for optimizing QLDBC designs jointly with the gate ordering design?
Yeah, I think, well, we should talk about it afterwards, so I can make sure that I understand correctly the question. But I think one thing that I didn't address here was what decoder we're using, which I think is relevant to this question. And I assume here that we are using a minimum weight decoder. And then everything that I said, I think kind of holds and makes sense. If you have a different decoder, maybe you care a little bit less about the maybe you care a little bit less about these things, but these things are still important. If you have your whatever decoder you use will be worse than this if you have a fault configuration that's lower than half the distance. So this will be perfect in that case. It's the optimal decoder in that case. So this will still give you some kind of bound on how well you could do for the low noise rate, low noise regime. So maybe that's, I don't know if that's useful or not. But, yeah. Sorry, Leonid, go ahead.
Yeah, so very superficial question, right? But before you get these bricks that you use for circuit design, so you have to come up with a set of valid circuits that don't end up producing measurement, sort of spurious measurement outcomes. Because when you are trying to measure X and Z generators at the same time, it's very easy to make this mistake. And then you will have...
Your circuit needs to be valid, yeah. You can, so that's actually, there's a paper where I cited earlier, which is the general form, for the general form. And that paper is actually about stabilizer circuit verification, which I think is, yeah, it's essentially tooling for that. Well, I have too many slides.
Well, you can use STIM to verify.
You can use STIM, yeah, you can use a number of different approaches to verify.
How do you come up with the good circuits? Is there general?
Well, I can tell you how I think about it, but yeah, I mean well, I can tell you the rules that I use whenever I'm like designing nitty gritty fault tolerant circuits. Yeah, after this is a secret. No, they're well known. I mean, just yeah. Andrew Landau has a really nice paper in the color code from 10 years ago or so now, where he specified, I forget who else was on the paper, but it was not a single author, and he specified the kind of rules that you need to build one of these kinds of circuits, and yeah, to ensure validity. And I think that's kind of like the nicest description I've seen of it. Thank you.
Yeah, so it seems like in this formalism, like you require like the faults to be all independent. But let's say you have some like poly channel that's with arbitrary probabilities for X, Y, Z, then like will it just completely not work?
No, that's included. Yeah, so you can have any Pauli operator has to occur with some probability, and the probabilities and the events should be independent of one another. But even there's you can show that if you have the circuit noise model, which formally doesn't work like that. Formally, you have an idle location, and if that location occurs, then either an X will happen, or a Y will happen, or a Z will happen. So they're not independent; they're exclusive events. You can map that to an independent model exactly by just tweaking the probabilities.
Probabilities for X, Y, and Z are all like different.
That's fine. Yeah. I mean, this is just for simplicity. I include. I included. There are some things like the definition of a distance, which you can think of as if you have a single noise parameter p and all of your error rates are proportional to that, is the order. It gives you the order of error suppression. P to the d over 2 will be your logical failure rate. So that part, it still holds. So yeah, I don't know if that's actually answering your question, but
yeah, but not okay. Yeah, maybe I'll ask you later. But
sure. Okay. Yeah.
Throughout your talk, I understand you consider innovate for matching decoder. So I think this kind of argument can be used for banding logical error rate. But if we replace this decoder to some other decoders like unifying, it suddenly happens that this kind of we cannot bound logical error rate. We don't have any proof techniques. You have some idea to like circumvent this kind of. I think it's a matter of proof technique, but is this to expect this kind of argument useful? Or
Yeah, I think there are certainly cases where the union find algorithm behaves precisely the same as the minimum weight decoding up to distance. Yeah, but that's all that everything that I described today is in that regime. So yeah, but there's also cases where that doesn't apply for the union find. If Nicola is here, does union find always achieve distance for any graph like?
For
Not just surface code, but like any graph like model. Maybe.
I think so, yeah.
Okay. So yeah, well, yeah, answering by deferring to people who know more. Okay. Maybe we could go get coffee and you can ask people can ask more questions in the break, if that's okay.
It's okay, we still have some time. So if there are any other questions? Yeah, let's take a break, and we